theory of special relativity has proved and also predicted that nothing can move faster than the speed of light. Yet, the theory of general relativity has also predicted and proved that the most distant galaxies are moving away from us faster than the speed of light. This is both true at the same time. And still, yet, relativity is one of the more logical theories in the field of physics. Let's get to know why. Let's talk about Einstein for a bit. Einstein was a revolutionary scientist, no doubt there. But how did he get to the concepts that he had? Let's try to think like him, okay, for a minute now. So, what Einstein was doing, Einstein was a patent clerk, and he was looking outside his window. And one day he saw the window washers coming towards the window, and then he just came up with a thought experiment. What if the person washing the window fell down? For most of us, that will be a very grotesque image of blood and splattering everywhere. But for him, he was just thinking about the falling. What if the person was falling indefinitely? What if there was no ground that he's going to crash into? And he kept thinking about that. And if there was no wind resistance, then the person falling perpetually would have been the same case with a person in weightless in space. They will have the same properties, and you can't distinguish between those two frames of reference. And that's the question that Einstein had. Okay, if we can't distinguish between those two frames of reference, then acceleration, it is accelerating down at 9.8 meters per second, right? And acceleration and gravitation are the same thing. Now, this was revolutionary for many reasons. One, importantly, being that Newton had proved that gravity was a force. It was a mysterious force that acts upon all masses, and time was constant, and space was constant, and reference frames are not. They are different. Those two reference frames are different. But Einstein neglected that thinking completely, and started to focus on this idea that maybe acceleration and gravitation might be the same thing. Okay, so then he thought about another experiment. Imagine that you are in a windowless room, okay, but you can't see outside, and in that room you measure your weight. For example, it's 67 kgs. Then that is the weight that you have with the force of gravitation of Earth, right? Here. Now imagine that we just put the same person in a spaceship, the same room in the spaceship, and that spaceship is accelerating 9.8 meters up in the upwards direction, or in any direction. There is no up or down with no gravitation. Then you can see that the weight measured will also be 80 kgs. So that proves our equivalence principle. That is what this is called, by the way. That acceleration and gravitation provide the same frames of reference. But there was another thing that he thought about, okay? Now let's not talk about weight. Let's go somewhere else. He said, what if I hold a torch? Now, if he is in a spaceship going upwards, when he turns on the torch, since light has a speed, it is not, infinitely fast. It will take some time to reach the other side of the rocket. That would mean that the beam of the light would be sloping downwards since the rocket is going upwards. All of this is a thought experiment, by the way. We need incredible speeds to actually measure this. But, that would happen. Now, if you are on Earth, that would not happen, right? That is not supposed to happen. If you measure a beam of light will not be sloping downwards. It will be going in a straight line. But then that would mean that the equivalence principle does not exist. That acceleration and gravity are two different things after all. But then he got the idea that, no, let's assume that the equivalence principle is true. And that means that light bends due to gravitation. And light bending due to gravitation that's the idea, that light can bend due to gravitation. He said, okay, light takes that path because that is the shortest distance. we initially thought that light travels in a straight line because we assumed that, light will take the shortest distance. And yes, light will take the shortest distance, but the shortest distance isn't a straight line. When you see a globe, the shortest distance between 2 points is not a straight line, it's a curve. Therefore, Einstein studied the curvature and mathematics of curvature and figured out that light does travel the shortest distance due to gravitation, and that is a curve. It does bend a little. And that was a mind blowing discovery right there. So, that was this, all of this that we are talking about right now. This is known as the general theory of relativity. Einstein realized that space and time are not two components that are distinguishable and have nothing to do with each other. They are two sides of the same coin, and gravitation is the bending of time and space. It's the curvature of time and space, and all of this can be understood via different frames of references. This theory is known as the general theory of relativity. He actually published this theory after the special theory of relativity, which is very interesting. I might tell you that the next video is going to be on that. But just today, right now, what we did was we just went to the thinking of what was going on. And that thinking, that thought process is important. So, dear science, thank you so much for, enabling us to think in more weird ways and getting to a beautiful structure that no one would have predicted. And thank you, Einstein, too. So this was a talk today about the general theory of relativity. Bye bye.